Welcome to The Explainer. Today, we're going to put on our detective hats and solve one of geometry's classic puzzles. How can you be sure two triangles are perfect clones? So, right off the bat, we've got our first case. You see these two triangles? They look pretty much identical, right? But here's the thing about geometry. Looks like just doesn't cut it. We need proof. Cold, hard proof. So, the real question is, how can we know for sure they're perfect clones without the headache of measuring every single piece? Well, the official fancy geometry term for these perfect clones is congruent. And really, it's a super simple idea. It just means two figures are identical in every single way. We're talking the exact same shape and the exact same size. Think of it like a perfect photocopy. You could lay one right on top of the other, and it would be a perfect match. So sure, we could prove they're clones the long, painful way. Whipping out a ruler and a protractor, measuring all three sides, then measuring all three angles, and making sure every single one of those 6 parts matches up. I mean, it works, yeah, but it's slow. And any good detective knows you've got to look for the shortcuts, right? There has to be a smarter way. And lucky for us, geometry totally has our back. It gives us this awesome detective's toolkit full of secret shortcuts. These are basically proven rules, theorems if you want to get technical, that let us prove triangles are congruent with way, way less information. And how many of these super powerful tools do we get? Just 5. That's it. 5 simple rules that can crack pretty much any triangle case you'll ever run into. And here they are, in all their glory. These are their code names: SSS, SAS, ASA, AS, and RHS. Each one is like a little recipe, a mnemonic that tells you exactly what pieces of evidence you need to find to solve the mystery. Okay, but here's where you got to pay close attention. The details really, really matter here. Take a look at SAS and ASA, for example. The position of the evidence is everything. For SAS, that's side angle side, the angle you find has to be the one that's literally sandwiched between the two sides you know. Same for ASA, angle side angle. The side has to be the one connecting the two angles. It's not just any side or any angle. Location is crucial. All right, enough theory. Let's see one of these rules in action. We're going to grab our SAS, side angle side tool, and crack open a classic case file. So, here's the setup for our mystery. We've got 2 straight lines, AB and CD, and they intersect. Now, the crucial clue we're given is that this point right in the middle, point O, is the midpoint for both of those lines. That's a huge piece of information. And you can see this intersection creates 2 triangles. Our mission, should we choose to accept it, is to figure out if these 2 triangles are perfect clones. Okay, let's break this down like a real detective. Step 1, let's look for our side evidence. The problem told us O is the midpoint, right? So that means the segment AO has to be equal to BO. Boom, that's our first S. And for the same reason, CO must be equal to DO. There's our second S. Step 2. Now we need an angle. And look right there at the intersection. We have vertically opposite angles. That's a classic geometry rule. It means angle AOC is always equal to angle BOD. And look where that angle is. It's right between our 2 sides. So that's our A. So what do we have? We've got a side, the angle that's tucked right between them, and another side. That is a textbook match for the SAS rule. Case closed. We can officially declare these triangles are congruent. Okay, hold on. We did all that work. We followed the clues, we applied the rule, and we proved the triangles are clones. Great. But so what? I mean, really, what's the big deal? What's the payoff for all our hard detective work? This is the best part. This is where we get our reward. It's like a superpower you unlock after you've proven congruence. It's a principle so fundamental and used so often in geometry that it has its own famous, kind of clunky acronym. CPCTC. Okay, so the full name, the formal definition is corresponding parts of congruent triangles are congruent. I know, it sounds a little repetitive, but what it means is the key that unlocks a whole new level of information. Let's just put that in simple terms. This is the real magic of it all. What it means is this. The second you prove 2 triangles are clones using SSS or SAS or any of those shortcuts, you instantly get to say that all of their other matching pieces are also identical, automatically. No extra work needed. This is the ultimate payoff. So think about our case with the intersecting lines. We only used 2 sides and the angle between them to prove they were congruent, right?
That's all we needed for SAS. But now, because of our superpower, CPCTC, we get the other 3 pieces of the puzzle totally for free. It's like a bonus prize. We now know with 100% certainty that the third side, AC, is the exact same length as BD. And we also know that angle A is the same as angle B, and angle C is the same as angle D. We figured out 3 new facts without measuring a single thing. That is a massive reward.
All right, let's close the case file. It's time for the final verdict. Let's recap why these tools aren't just for geometry class, why this whole process really matters. So here are your key takeaways from this investigation. First off, these rules are a massive shortcut. They let you prove triangles are identical with just a few pieces of info instead of all 6. Second, they unlock hidden facts. Once you prove congruence, CPCTC lets you discover all this other stuff about equal sides and angles you didn't know before. And this is maybe the biggest one. This is a foundational skill. These rules are the building blocks for way more complex proofs down the road. It's basically logic in action. You're learning how to prove something is true with certainty, not just because it looks right. So now you've got the toolkit. You're a geometry detective. The next time you look at the world around you, at a bridge, a building, even a slice of pizza, remember these tools. What hidden truths can you uncover in the shapes that you see every single day?